and welcome to the June 2024 NASA Night Sky Network member webinar. I am Kat Troach here with my colleague Brian Cruz, and we are hosting tonight's webinar from the Astronomical Society of the Pacific in San Francisco, California. And we are very excited to welcome our guest speaker, Kim Steadman, with her talk on Perseverance 3 Years Exploring Mars. And before we introduce Kim Steadman, I do want to just make some quick announcements. We are closed for the summer. That's it. That's the announcement. We are not, Night Sky Network will be taking July off, so we will not have a webinar for July, but we will have, member news, and we'll have some updates for you via email, but there will be no webinar for July, so I don't want anyone to think that they missed something in their inbox. We will return in August, on August 7th, for a webinar with our team from International Observe the Moon Night. However, we do have a webinar, or rather a meeting, this Tuesday coming on July 2nd, and that is with our partners at the Museum and Informal Educator Alliance. And it's kind of a follow-up to tonight's webinar, and we call it Cosmic Conversations. So if you had any questions at the end of this webinar that you just were desperate to get out and you wanted to learn a little bit more on, you can go ahead and register at the Zoom link I'm dropping in the chat right now for next Tuesday's webinar, and that'll be at 5 p.m. Pacific time, 8 p.m. Eastern. So make sure that you get signed up for that. Do you have anything you want to add, Brian? Is there anything else going on?
Yeah, just one note. I just wanted to note that Vivian is on kind of an extended sabbatical. She will be back in August, so she's been out for a few weeks, and she'll be out for a few more weeks. I'll be out for most of July. Kat's going to be out for a good part of July also. And if she hasn't told anyone before, she's going to Chile as a part of the ASEP program and, learning how to do more and better astronomy. And so congratulations to Kat for being accepted into that program. It's going to be a great experience for you.
Thank you. I appreciate it. I did just have one more update because we did get some email inquiries. The new Night Sky Network internal website is coming. It should be, we're hoping by the end of August, it'll be released for everyone to finally use and enjoy. So just be on the lookout for that email. It will be happening soon. All right, so let's go ahead and get started. So again, for those of you on Zoom, make sure that you're set to everyone. And please feel free to greet each other in the chat. You can also email us at nightskyinfo@astrosociety.org anytime if you have any questions, if you have any comments, any concerns. And if you are going to ask a question throughout the chat or throughout the webinar, make sure you use the Q&A window so that this way we can see your question. And tonight's webinar is brought to you by Kim Steadman from NASA JPL, and it is Perseverance, 3 Years of Exploring on Mars. Kim Steadman received both her Bachelor of Science and Master of Science in Aerospace Engineering from Georgia Tech. After graduate school, Kim started her career at NASA's Jet Propulsion Laboratory. While at JPL, she has worked on several missions, including the Mars Exploration Rover Mission, Cassini-Huygens Mission to Saturn, and Mars Science Laboratory, and the Mars 2020 rover. Currently, Kim is a systems engineer for the Mars 2020 rover and the Technical Group Supervisor for the Integrated Planning and Sequencing for Surface Missions Group. As a systems engineer for Perseverance, it is her job to enable science while keeping the rover safe and happy. She is also the role lead for the campaign implementation systems engineers. In her job as a technical group supervisor, she manages a group of about 20 people who support operations for the current surface missions at JPL. And in 2015, Kim received the NASA Exceptional Achievement Medal for her work on the Cassini Solstice program. When you're ready, Kim, take it away.
Oh, hey, I forgot I wrote all that. That was a lot to say. Thank you very much.
No
Okay,
problem.
yes, I am Kim Steadman, and I got my degree in aerospace engineering, and so I will be talking a little bit about science here. But remember, I am an engineer, and I have done science systems engineering, but still an engineer who will try to answer your science questions if I can. Let me see if I can actually share, because sharing is caring. Okay, so can you guys see my screen?
Yes.
All right, cool. So yeah, so currently I work on the Mars 2020 rover, better known as Perseverance, or as we like to call her, Percy. And I am a tactical uplink lead. The uplink process is the process that we come in and do every day that we want to send stuff to the commands to the rover. And we come in the morning, we what she did the day before, and then we prepare all the sequences and file loads that are going to enable her to conduct science and do drives and unstow her arm, whatever we want her to do the next day. And at the end of the day, all the sequences and file loads are ready and they get sent to the rover. And it's my job to make sure that this all happens in a timely manner, because I think I just fell off the internet.
We have you back now.
I know. It did this to me earlier. I don't know why. Let me try and share again. Okay, let's try it again, and hopefully the internet will like me. So I'll move faster so the internet won't cut me off. Okay, so today this is actually an image from Curiosity when she got stuck in Dingo Gap. But this shows you what Mars looks like today. Today, Mars is a cold desert with some beautiful rocks on it. Ancient Mars, about 3.6 billion years ago, looked a lot like Earth. And so that's what makes Mars so intriguing to visit. First of all, she's close. And second of all, she used to look like us, but now all right, I think I'm back again. I don't know what's going on.
Okay,
I'm going to turn off my video to see if that helps. So
Okay.
you guys hear me and not see me, which is really great for me. Let me try that again. Share. Advanced.
so we're seeing your presenter view.
I know, I'm fixing it. If it'll take it, please take it. My internet looks all right. There we go. I think maybe without my video, it might be a little better. Okay, so we're back at Mars. Mars 3.6 billion years ago looked a lot like Earth, but now today she's a desert wasteland. But the good thing is that her history and geology is still there, and it's just waiting for us to come and show up and read it. And so whereas Spirit and Opportunity, their mission was to follow the water and figure out the history of water on Mars. And then after her, we sent Curiosity. And Curiosity's job was to figure out if Mars was ever habitable, not whether there was ever life there or not, but whether the conditions for life ever existed on Mars. And she found that they did. And so as a follow-on, we sent Perseverance. And one of the goals of Perseverance is to look for microbial biosignatures. So we're not looking for fossils that look, like when you go to the fossil store, you see these really cool fish or ferns or these little bugs. We're not looking for that. We're looking for microbial biosignatures that have to be seen with really precise instruments. And so the instruments that we've sent along with on Percy is we have at the end of her arm, we have what we call the proximity science instruments. And these are instruments that get just a few millimeters away from their surface to do their science. And Pixel is our X-ray spectrometer, and Sherlock is our ultraviolet spectrometer, our Raman spectrometer. And so with Sherlock, we are looking for organics and minerals, and Pixel is telling us the chemical elements that are contained in the rocks. Along with those, we also have Meta, which is our weather station, can tell us the wind direction, how strong the wind is, the temperature and the humidity on Mars. And we also have SuperCam. SuperCam has 2 lasers on board, and so she can tell us about the minerals that are in the rocks, and she can also tell us the chemical elements. But she has to work about 20 feet away from the rocks because she's up on the mast. We can't really touch her down. So when we get into an area where we can't put down Sherlock or Pixel, or we just want to do more work than more observations than we can do with Sherlock and Pixel, then we use SuperCam. So if we're just stopped for a day between drives, we use SuperCam a lot. And so we can actually fire both of those lasers at the rocks in front of us. And she also has a micro imager. And then up on the mast with SuperCam is Mastcam Z because it's our first zoom camera that we're actually sending to Mars. And so she's our panoramic imager. And on the back, we have a subsurface radar instrument called RIMFAX. So as we drive the rover along, RIMFAX looks into the surface to tell us what everything looks like below the surface. And MOXIE, we don't use MOXIE anymore, but MOXIE was a test technology project to see if we could breathe in Martian atmosphere and then pull off the oxygen and save some oxygen. That I guess you guys all saw the Martian, where he had his oxygenator, and that's sort of this kind of technology. And so it proved really well. It worked, and now she's been retired. We also have inside of our rover, inside the Curiosity rover, are some chemistry labs, but inside our rover is a sampling and caching system. And it's a very complex thing, and it's actually open on the bottom. But we have a drill on the end of our arm that also has Sherlock and Pixel. And it's a coring drill, where the drill on Curiosity just brings up fine dust that we can feed into those chemistry labs that I was talking about. What we're collecting is a core. And so here's the coring bit. And then we also have an abrade bit. If you remember from previous rovers, they had a rock abrasion tool, because these rocks have been sitting on Mars for billions of years waiting for us to come and sample them. And we really want to sample the interior of the rock. So what we do is we abrade away about 9 or 10 millimeters of the surface so that we get this nice, really flat, beautiful surface that you see on top that is really, really a really nice space for us to use Pixel and Sherlock. And if we're doing our coring and caching, this is what it takes to do it. Here's our sample tube over on the left. If my video was actually working, I could show you a sample tube, but they're very small. And in the middle is where we get our core. And it's a very small thing. You can see up here, when we get a core, it is not very large at all. And so we're doing a lot of work for these itty bitty samples, but if we can get those back to Mars, the scientists are going to learn so much more than we can with our rovers. So we took with us 38 tubes for rock and regolith. Regolith to me is just dirt, and 5 witness tubes. And the whole purpose of the witness tube is we put the witness tube in the drill, just like we would a sample tube. And we go through the whole drilling process, except for putting the drill down onto the surface. And this just gives us witness of what kind of contaminants or what else we're getting in the tube besides the actual sample that we're taking from the rock. Okay, now that we have our rover explained, where did we send her? Well, we sent her to Jezero Crater. And the reason that we sent her to Jezero Crater is, if you look right over here where it says Jezero Delta, there is this huge delta and an inlet valley. So if you're a geologist, you look at this and you say, here is where a big river came into this crater. And as the river was flowing into this crater, it formed this huge delta. And then eventually at some point, Jezero Crater filled up with water and the outlet valley went over here. And so perhaps 3.5 to 4 billion years ago, this might have been where we could have found life. And here's just this is from the HiRISE camera on the Mars Reconnaissance Orbiter. It's just a beautiful shot of the delta in Jezero Crater. And you can easily see where the river came in and formed this just huge delta. And then somewhere after this delta was formed and water was long gone, then we got a little meteorite impact so we can have that cool looking crater right there. So this is just to show you a river delta in Alaska and here on Earth. And so at one time, this is what was happening on Mars. And you see all these beautiful colors here, and that's just life. And so river delta is a really great place to go looking for life, even if it's really, really old. So we landed on February 18th of 2021. If you remember, that was during the lockdown. So that was joyous fun. But if you haven't seen it, you should go watch our landing video. Just go to the Mars 2020 website or even type in your Google Perseverance landing, and it's really cool. But today we're not talking about that. But where did we land? Here's where we landed. Here's our delta. Here's the inlet valley. Here's the edge of Jezero. And we landed right down here on their crater floor. And they named it the Octavia E. Butler landing site. So if you've ever seen names of all these places on Mars, except for Octavia E. Butler landing site, and wondered how we name them. So every target that we image, every rock that we shoot with SuperCam, they all get names. And how do we come up with the names? Well, the scientists, way before landing, took took our landing area and where we might spelunk to, and divided it up into these different areas, and then gave each of them a name. And so these are all national parks somewhere all over the world. And so when we're in these quadrants is what we call them, or in the quadrants, like we're in the Rocky Mountain quadrant, all target names are going to come from the Rocky Mountain area. So when we're in places like Rocky Mountain, those of us who are, from America and everything, we can pronounce everything. When we get into some of these other areas, it's not so fortunate. So that's where our names come from. And this is what we did with our first 1,000 sols. So we landed down here on the crater floor. And from way before the rover was even built, the scientists had come up with this idea that our whole mission would be broken up into what they call campaigns. And so it'd be a campaign would be the science in a small area, so that this overarching group for that campaign could decide what all the science goals were for that area, and then come up with a list of things that we have to do before we leave that area. And then the operator, the science operations person, could make sure we hit all of those before we left. And so we ended up with a crater floor campaign, the Delta front campaign, because this is the front of the Delta here. And then once we got up on the Delta, they called it the upper fan campaign. And the most confusing name is the margin campaign. I'll show you why they call it the margin campaign. So Jezero crater floor. Our whole purpose here was to figure out what is a crater floor made out of? Where did all these rocks come from? Were they deposited by wind? Was it water that was in Jezero? We know water was there. We see all the evidence. And what kind of rocks are we looking at? Are these sedimentary rocks? Are these, is this a lava flow that cooled off? And we really had no idea. And the more we looked at things, actually, we didn't have much, resolution to that for quite a while. It took us a while to get enough different areas sampled to figure out what was going on here. But one thing for sure that we knew, that these are probably the oldest rocks we're going to find while we're in Jezero crater. Once we leave Jezero crater, everything's going to be about 500 million years older. But while we're in Jezero itself, this is where we wanted to look first, to learn about the crater's history before the delta was formed. Then once we moved up to the delta front, the front of our big giant delta, we knew this, again, this is the oldest part of the delta. And because we're at the end of the delta, these are the rocks that might be the most likely to contain signs of past life, if it ever existed. And this strip of, that you can see the bright strip right here, from the air, it looked like a big strip of bacon. So for a while, that's what we called it, the bacon strip, because we're really, really original. Then once we finished with the Delta front campaign, we got up on top of the Delta, and we called that the upper fan campaign. And so what we're trying to learn up there is the Jezero River when it came in. What did it bring in? Was it a fast moving river? And we also know that it would bring rocks from outside Jezero into here. And when we're in the upper fan campaign, that's where we would see these rocks. So this might seem a little basic, but it's nice to throw in here. So the history of Jezero. So about 4 billion years ago, a meteorite hit Jezero and created it, or hit in this area and created this giant crater. And up in the right, this is actually a crater from the far side of the moon that's 75 kilometers across, but it looks a lot like Jezero without the delta. So this is what Jezero probably looked like way before the river intruded on its life. All right, so the first thing we did, of course, was a crater floor campaign. And so we started looking around in our immediate area. And one of the first rocks that we actually abraded, that's where we use our drill and the abrade bit, and we clear it off and get down about 9 or 10 millimeters so that we have this beautiful surface for Sherlock and Pixel. And so first what we do whenever we're going to do any kind of sampling or any kind of proximity science is we use our other instruments to take information from the area so that if we get our samples back, then the scientists have context. We know what the rocks in the area look like besides just the rock that we're sampling. We have Mastcam Z imaging 360 around the rover. And so we used our SuperCam RMI, the remote microscopic imager, and you can see that's a beautiful picture there. And so we did that. That's before we did the abrade, the SuperCam RMI. And then over here on the left is our abrade. And this image was taken by the Watson camera, which of course, if you're going to go to Mars and you take Sherlock, you have to have Watson. So there's 2 bore sights on the Sherlock Watson instrument. One of them is the Sherlock spectrometer and one is the Watson imager. Watson is an almost exact duplicate of the Mars hand lens imager, which on Curiosity. And so some of our first Sherlock analysis. So Sherlock, so the scan area that you see there is about the size of a postage stamp. And Sherlock, all those little dots are different Sherlock readings. And so Sherlock will fire the laser on each of those dots 100 to 500 times when we're taking one observation. And this is the information that we get back of exactly what's in this rock. And so here we can see that we had olivine, carbonates and olivines mixed. And this is also, we saw organics. That's the whole reason that Sherlock is there, because Sherlock can see organics. And so you can see over here in the smaller image, the area where they detected the organics. And so this is the first detection of organics on the Martian surface since Curiosity rover. And I think when Curiosity saw her organics, she was still in Gale Crater and hadn't started climbing. And this is also the first time that we've seen organics on a Martian surface with ultraviolet fluorescent spectroscopy, because this is the first time we've sent a spectrometer that works like Sherlock does. So it was determined that these organics are not bioorganics. They are non-biological. They were formed by non-biological geological processes. But still, we were very excited to see organics because that's one of the things we came for. And remember, what we're trying to do is figure out what the rocks are made of and the crater floor. And so every time we would get an abrasion until alfalfa, everybody was like, some of the scientists, it's sedimentary rock, and others, it's igneous volcanic rock. And so when we got alfalfa, it became pretty obvious to everybody that what we had on the crater floor was, in fact, igneous rock of volcanic origin. And so I don't know, I was very relieved because every time you called into a science meeting, it was half of them sedimentary, half volcanic. And so once there was clear consensus that we had volcanic rocks and that at one time the whole crater floor was filled with volcanic rocks. So then the question was, we were seeing these volcanic rocks, but they also had, some of them were cumulative rocks. And so they are igneous rocks formed by an accumulation of crystals from a magma. And so this is the first time we'd actually seen this on Mars. And so everybody was like, well, how did that happen? And so the determination was that you had all this magma and then it cooled very, very slowly. And so as things came into the area on top of them, and we ended up with these really complex rocks, which is what made it so hard to figure out exactly what they were. And the Sita formation, on top of this dark formation was actually a bunch of sand dunes. So that's why this is the white line is where the rover went. And so that's why the rover had to go all the way down to the bottom and then come back up, because this area over here where you see the little blue dot, that's where we did our abrade and sampling that really gave us the key to unlock this whole area. So now that we've done with the crater floor, now we're going to go and look at the delta front and the upper fan and the margin unit. And so everything was telling us that 3.5 to 3.7 billion years ago, there was a lake here with a river coming in and a river going out. But that doesn't really tell you the whole story. As we started exploring more, we found out that there are like kind of 3 chapters to the story of water and Jezero crater. And we'll go to the first chapter. And so when we got to the Delta Fan and places, wonderful names, Hogwallow Flats, Devil's Tanyard, we saw thinly layered sandstones. So what had happened, and Gale Crater, where Curiosity is, there's a lot of fine grained sand, rocks, and mudstones. And when we got here, we saw them, but mostly on the delta front. We didn't see them as in the abundance that Curiosity has seen them. And so at one point, of course, when Jezero was first formed, there was no water. Somehow, eventually, a river reached the crater rim and flowed into Jezero. But at first, it didn't build a huge lake. It was more of a seasonal. There'd be small seasonal lakes. You would have water for a while, then you wouldn't have water. And then the next season, you would have some more water there. And so that's how these flat paver stones are formed from the fine-grained sand that was brought in. And so, and here's another view of the intervals of soft sediment deformation. These were all over in the area. And so that gave us, when we were in the Delta Front, that gave us our chapter 1. So chapter 1 of Jezero water started with a river that comes in and has seasonal lakes. So I just want to show you guys some rim facts, because I did tell you about rim facts. But while we're trying to figure out how everything formed, when it formed, one thing that has really helped is being able to see underneath the surface. And that's what RimFacts does. So as we drive along, RimFacts is taking readings the whole time. And so we've been able to figure out exactly when these layers, which layers were formed first and which ones are covering the others. And so it's just a little bit of the data from that. You can see that here's the CETA, and then we have those pavers that we're just looking at. And there's light tone and dark tone pavers up here. And over here is the delta. So the delta is on top of all this. Then we also saw some really interesting stuff that got some really cool names, like Upper Rocky Top. And you can just see this looks a lot different than anything else that we have seen. Because when we're in the crater floor, we do see some delta remnants off in the distance, but we didn't see anything that looked as spectacular as this. And some more, and here's what, so right below Rocky Top is this, what we've been looking at. And then we found this. So this is a giant outcrop called Pine Stand. And so what Pine Stand shows us, as you can see, just looking at this, you can see all the layers started forming from left to right. And so this told us that as the lake grew, the lake eventually got to be 35 kilometers in diameter and as deep as 100 feet. So the different layers that you see here, you sort of have a light layer and a dark layer and a light layer and a dark layer. And so some of these are 10 meters thick. And that's pretty big. And so to cover all of this up, you're about, it would take 100 foot deep river or lake to cover this up. And so you can see as it built up over time, and eventually this was all covered by the lake. And so this is our second chapter, when Jezero crater was full of a lake that stayed there for a while. It built up, making all these layers, and then it was just a nice lake for a while. And our chapter 3, when we got up to the close in the upper fan part, getting close to the margin, we saw boulder fields. And this was incredible. And it's hard to tell scale here, but some of these are like a meter across. So these are pretty big. A lot of these are pretty big rocks. And they caused a lot of trouble for us driving the rover, because the rover can drive over smaller rocks, but not the bigger rocks, because she could get stuck. And so the way that these boulders came in was a fast moving river. So we had a lake, and now we've got a fast moving river coming in, and they're carrying really, really large boulders. And that's just a close up because it's just really cool. And imagine driving through there. So then when we got up to the margin unit, we did a little Pixel and a little Sherlock. And this is at Ozul Falls. And this is Bill's Bay abrasion patch, because we have to name everything. And so what we saw here, if you look in the bottom left, you see the silica is in green and the carbonates are in purple. So what you had was a rock that was very happy, and the silica has wedged its way into the middle of the rock. And the good thing about that is silica and a carbonate is an excellent place, if life ever existed, for that evidence of life to be locked into this rock. And so that's what everyone was hoping for when we got to the marginal unit, and that's exactly what we found. And so we took a sample here, and that sample is still on the rover, and hopefully it will get to come home. And when it does, then we have a really good shot at, if there ever was life, hopefully finding some proof of that in this rock. So that's a brief overview of our science on our trip through where are we? We're at Sol 1176, and all of that was just from the first 1,000 sols. So my job is more of just figuring out how to do stuff and get the science back. And sometimes that can be challenging. So one of the things that the scientists really wanted to do was sample a conglomerate rock. The problem with a conglomerate rock, as you see down below, is they're a little crumbly. So on the left and the right, these are attempts at abraded patches. And the right one turned out better than the left one. But you can see how crumbly they are around them. If you remember the abrasion patches that I showed you earlier, they were really solid and you didn't have all these crumbled rocks everywhere. So even though we looked at these crumbly rocks and said we might not be able to sample there, the scientists wanted us to try. And so because we knew it was a really crumbly rock, we repositioned the rover, because to get a sample, we have to put the drill down, and then we have to pick up even though it has a piece on the bottom that's supposed to keep the sample from falling out. If it's not a really good, solid core that we have in the sample tube, it can fall out. And especially if it's really dusty, it just falls right out. So to increase our chances of success, we moved the rover to a different orientation so that when we pick the drill up, then hopefully nothing would fall out. But the first time we only had 2.5, or we only had a couple of rocks in there, and we really want 6 centimeters of a sample. And the minimum that we're going to actually seal and save for hopefully returning to Earth is 2.5 centimeters. And so we tried again. And we got even less on the second try. We got just some dust. And so we said, no, we cannot sample here, and let's move on. But so we were here at Uzu Falls. And so they're like, okay, we'll just go right over here to Emerald Lake. The rocks look the same. Let's give that another try. So each of these dots is like the end of drive location for the rover. So you can see we puttered around in here for a while looking for a better rock and didn't really find any. So we ended up over here at Emerald Lake. And in Emerald Lake, we actually had success. And so we had at Otis Peak, we had our conglomerate, and you can see there, it's really beautiful. And so up on the bottom top right is where we were, and then where it says Mount Meeker and Falcon Lake. So where I showed you all those boulders, this is the boulder field. And of course, the scientists wanted to sample one of those boulders. And so here's a boulder that we had pulled up to in the Falcon Lake area. And you see how close the rover is to it. So this is from the front has cam on the rover, and you can see the rover front left wheel there is really close. And so we were a little too close to this rock, and it was a weird shape. And we put the rover down, or put the arm down on it, but we couldn't get the right orientation so that it was actually safe to drill. So what we did was some natural proximity science on it. So we can actually use Pixel and Sherlock on a surface that hasn't been abraded. It just doesn't give us good results. So we did a little proximity science on that. And while we were doing that, we imaged around the area, and the scientists found another target that they wanted to try and sample. This really odd looking, looked totally different than anything around here, target called Mount Meeker. And so we drive the rover over to Mount Meeker, and on the left, you can see the abraded patch that we did on this rock. And it looks a little different again. Where we were, the conglomerates were really crumbly. This looks like we have barely scratched the surface. And so we're like, this is a really hard rock. We're not sure we can sample here. But that never dissuades the scientists from actually wanting to sample here. So we gave it a go. And as you can see, there is our, this is a really good shot too, to show you what it looks like when we drill. The two outer silver things are our stabilizers. And so when we go to drill, we put the arm down with the stabilizers on the rock, and then we feed out the drill so that we can drill the rock. And the stabilizers are there to keep the drill bit from walking while we drill. And so we tried to drill there. We gave it a go. And this is the end of our drill bit. And as you can see over here on the left, we lost a tiny nick out of our drill bit because the target on that rock was named Dragon's Egg. And so we tried to drill a Dragon's Egg, and it totally didn't work. And so this drill bit is actually still usable, even though it loses that little nick. We can still use it. It's not a problem. In fact, we took several. Here's all the drill bits that we took with us. The one on the left, the taller one, that's our regolith bit. And so you can see it has holes here. And so you put it on the end of the drill, put it in dirt, which is what regolith is. And we kind of move it around so that it gets all full, and we pick it up and shake it a little. So gets all the dirt impact to one end. And then we go ahead and seal up that tube. And then we have 6 chlorine sample tubes and 2 abrasion bits. And so even though we've nicked one of our chlorine tubes, we just used a different one. We have another chlorine tube that we've used before, and it's got some rocks stuck in it. So we've taken it out a couple of times to try and shake the rocks out of it, and so far, not much success. But we've still got others to use, so we're still going well. And now I'll talk just a little bit about driving. This is the crater floor. And if you can see it down the bottom right, you can see where it says Octavia E. Butler landing site. So that's where we landed. And then first we went south, we went around Setah, and then we came back. The scientists decided that they were ready to get over here to the Delta, over here where it says Three Forks and Hawksbill Gap. And so we wanted to go from around our landing site all the way over here as fast as possible. And so in the first 13 months of the mission, we'd driven about 5 kilometers. And then when we did our rapid traverse campaign, we did 5 kilometers and just 31 sols on Mars. And a couple of those sols we didn't even drive. So I think it was really only like 27 days of actually driving. And the reason that we had to go all the way around is that stuff in the middle has a lot of sand dunes, the Setah, and we can't drive there. We would get stuck and be very sad. So we went all the way around. And so what enables us to drive so far is this thing called auto nav. It's auto navigation. You kind of tell the rover where you want to go and give her, more than she can possibly do in the time that you've allocated to her, and then she picks her way. She takes images as she drives, and she compares them to the images she just took and decides if she's going the right way and where she should go. She's got onboard navigation software that as she's driving, is processing all those images that she takes and then is picking a way through that area. So we can sort of give her, 2 or 3 hours to drive and set her off on her way, and she'll go. But this is what happened when we got up there where all those boulders were. Like I had said earlier, each of these white dots is an end of drive location. So you can see some of them, she just didn't go very far. And so our goal was to get out here through the Dunraven Pass, because we cannot drive over sand ripples. Like these big giant ripples, can't drive over them. So we have to go the long way over here, cross at a safe point, and then extend on. And when we were heading towards an area called Bright Angel, because it had some bright rocks around it. And this is the Yellowstone quadrant. So we've got Dunraven Pass and Bright Angel from Yellowstone. So 200 sols to go 2 kilometers. And I'll show you what some of that looked like. So the white lines are the path that the rover chose to take. So what she's trying to do is find a safe way through all these boulders so that she can get where we're trying to tell her to go. And so sometimes she just doesn't go very far. She wanders around until she runs out of time in her drive. And so you see sometimes she just kind of goes back and forth. Over here on the left, she did a giant circle, and you see we did that circle twice. And each time we would do a short directed drive. A directed drive is where you give specific instructions to the rover that tells her you will turn the wheels to this angle, you will drive this far, then you will turn the wheels to this angle, and you will make this turn, and you will do that. So very specific, like if you were actually programming exact every wheel turn that she's doing. And so what we tried to do several times was do a directed drive out of the area that she was getting stuck in, and then try to go to auto nav. And so a couple of times in this bottom left picture, she would get out of the rock area that she was in, and she would get confused and just do a loop back through the rock area she was just in. So, and you can see she did a loop-de-loop up on the top right. So with the driving, we had to actually discontinue use of AutoNav for that whole area and just go with directed drives. So whereas when we were doing the rapid traverse, we could do, in one weekend, we drove 500 meters. When we were having to do these directed drives in the boulder field, we were making 20-meter progress in a weekend. So another thing that we've run into starting back in January of this year is our Sherlock cover. Sherlock is our Raman spectrometer that's on the end of the arm. And she has to protect the camera lens, she has a cover, and Sherlock has an auto context imager and the spectrometer inside the instrument. And so both of them have a focus wheel, because believe it or not, you have to focus your spectrometer. And the focus wheel would spin until we got to best focus. She could determine when best focus was, and that's when we would take our auto context images, and then we would do our spectroscopy. But after one of our operations of Sherlock, we always take images after we use these instruments. We just stick the arm out and use either the nav cam on the mast of the rover or the Z cam, the mast cam Z, to image to make sure that the cover has closed, even though we have contacts that will tell us whether it's open or closed. The Sherlock was telling us that it was not closed. And when we first looked at it, it looked closed. And then we imaged it more and noticed it was not closed. And so we commanded the cover to close. And instead of closing, it opened a little more. And so we took a little time to look at that. We had a Tiger team go off and do some experimenting in our test bed and look at historical information from the Curiosity rover, because this is the same cover that's on the Molly and the same cover that is on the Watson. And they came back and we shook the arm. We used the percuss on the drill, which kind of vibrates the arm, because we thought maybe we have some FOD stuck in this cover. And so we percussed, we commanded the cover closed, we commanded the cover open. We had the arm flip Sherlock upside down and see if that, and then commanded open. And for months we did this. And finally, one day the cover opened more, and then it finally passed 180 degrees so that we could try to reuse the Sherlock instrument again. So we went, gosh, this happened in January. So we went about 5 months where we couldn't use Sherlock. So if we did any abrade patches or any sampling, the only proximity instrument we had to use was Pixel. And so our last abrade patch that we did, we actually got to do Sherlock on Mars for the first time, and they got some spectacular data, which is really nice. So this is just an overview of where we've been. Each of these little orangey little blobs are where we've taken samples. And here we are up here. Here's the final resting place of our helicopter. And what's next? Once we finish up our margin campaign, we're going to exit Jezero Crater And once we exit Jezero crater, all the rocks we see will be 500 million years older. And that's our next step. And here, this little yellow line is our path outside of our exit path to leave Jezero crater. And the front here, closer to the camera, that's our margin unit. So here's this isn't up to date completely because we did another sample not long ago, but here's our sample collection map for tubes 1 to 21. And you can see where all they came from. And these are the abraded patches. No. Yeah, some of them are abraded. These are the abraded patches along with the actual end of the sample tube once we got the sample. Here's our first sample, Rubion. Told you that sample can fall out, and that's what happened there. Here's everything but one that's on the rover right now. Here's our samples and braid patches from the crater floor, the delta front, the upper fan, and the margin. We have done one more sample since this was created, and this is everything that's on the rover. At one point, while we're still down in the crater floor, we did drop 10 of our sample tubes as just a backup in case something happens to our rover, because we're driving around with the samples inside the rover. And so we recreated a sample cache so that if something happened to the rover before more sample return was on its way, that there would be some samples that they could go and collect. And that's all I have.
All right. Well, thank you very much, Kim. We have a lot of questions to go over, and we've got about 15 minutes. And so let's see if we can get to some of these. We had a couple of questions very early on about the cameras. One of them was, is the let's see, the panoramic camera on the mast seems to indicate that maybe it's a stereogram camera. Is that true?
And I think I'm back.
Okay, you're back.
There I am. Yay!
Yay!
Sorry about that. My internet was fine all day.
Yeah, and then all of a sudden, of course, that always happens. So the question that we had there was the one image that you had seemed to indicate that there were two arrows coming out from it, and so we're wondering, is it a stereo camera?
Two arrows coming out from, I'm not sure what you're talking about. Is it? Oh, are you talking about super cam?
Yeah, the mast cam.
Oh yeah, there's two mast cams. So there's, yeah. So there's mast cam left and mast cam right. And that's why. And they do take some stereo images, yes.
Okay. And then are the images that are returned, are they in true color, false color? So what are we looking at when we look at them on the website?
If you go to the raw images site, those are just as they come off the rover. And then when they do a public release, when they do a release of an image, usually they've gone in and done some coloring to that to kind of enhance what they're trying to show you.
Okay. Then we had a couple of questions from a couple of different people about the sample tubes. And so what's the current status of those? What's the plan to pick them up? What's the latest on that?
Well, the sample tubes that we put down in Jezero and on the crater floor, right now, as far as I know, there's no plans to go and get those. Mars sample return as a mission is kind of in flux right now. I think NASA is soliciting designs from industry and from JPL for what a Mars sample return would look like.
And we had a really great question earlier on about spectrometer. And so when you're using the spectrometers, this was very early on when you were talking about this. How would you differentiate between organics coming from comets or asteroids versus any past life on Mars?
Well, of course, a spectrometer can't really tell you where things came from. They can just show you what is there. And so it couldn't actually differentiate like that. It's just telling you what we found there. We're hoping to, if the samples come back, then we can have more instrumentation and more scientists looking at them and trying to figure that out.
And that's something from what I understand, it's relatively straightforward at making a comparison between the different isotopes within the minerals. Is that correct?
The stuff that I have seen for sure, I was a Sherlock ops lead for a while, and the scientists did a lot of, before we even sent Sherlock to Mars, they did a lot of characterizations of everything on Earth. And so they have all these plots and a nice, beautiful tool that kind of highlights the peaks. And then from comparing that to the data that they've taken on Earth, then they can, that's how they're determining what each of those peaks in their spectrometer is, what it actually is. But still, sometimes things aren't easy to read for them, and they have debates on exactly what they're seeing. And so there's people that they spend their whole time just trying to look at some of the Sherlock and the pixel data and trying to come up with what it means. And a lot of times to figure everything out, you have to look at the Sherlock data, you have to look at the pixel data, and then you have to look at some of the remote science data that we get that kind of puts everything in context. Okay. So it's not, I thought when I was the ops lead, I thought there's going to get this down and it's going to be like, this is X, that is Y, that is Z, this is obvious. And it doesn't seem to be that way.
So I know that there are many different types of spectrometers, including mass spectrometers, and is one of the there's just the one spectrometer on Perseverance, I take it, and it is not a mass spectrometer that differentiates between isotopes. It's one of the other types that just has kind of a more general. This is what the mineral is. Is that correct?
We have two spectrometers. One is Pixel, which is an X-ray spectrometer, and then Sherlock is a Raman spectrometer. Okay. And so the Sherlock is really cool because it fires its laser, and it's like a donut. So if you, I don't have one of these images, but when we do a natural surface with Sherlock, you can actually see the ring that the laser makes when it hits, because it's a donut. It's not like just a solid point. It makes a little donut. And so when that is reflected back up to the Sherlock instrument, that's how it gets its data. Okay. And so we use Pixel, the X-ray spectrometer, is supposed to tell us the chemical elements, and the Raman spectrometer from Sherlock is supposed to tell us the organics and materials. Okay. I haven't looked at much of the pixel data besides what I showed you, and I haven't been in the room where they're debating their results, but I know for Sherlock it was sometimes obvious what they were seeing, and other times they really had to dig into it and futz with the data, and then they'd have to get together and agree on what it was.
Okay. I guess, the hope is that eventually those samples are going to come back to Earth and they can apply the, additional analysis to them and really delve into what they are.
That's exactly right. And one thing that they're using Sherlock and Pixel for is we do the abrade, and then we do Sherlock and Pixel, and then the scientists look at that, and then they decide if they want to sample. They have sampling, if they're interested in that area, they're interested in that rock, sampling may be in what we call our sol path, like we're planning to sample. But usually the scientists want to look at the Sherlock and Pixel results to decide for sure whether they want to take that sample. They have to see something compelling in Sherlock and Pixel results to go ahead and take that sample.
And kind of sticking with the idea about the samples, we had a question about what is it that's making the conglomerate rock so crumbly? Is it like it sounds? It's a bunch of different types of materials that don't bind together well. And they also asked as part of that, how did water play a role in this conglomerate being formed? And is the water still there? Are you able to see signs of water that continues to be there?
And Jezero crater, we have not seen that at all. We've seen a lot of rocks in Jezero that, of course, have been altered by the presence of water. And the conglomerates that we've seen have just been really crumbly. They're more like a sandstony type material. And at least that's what they look like. And yeah, they're just very crumbly. And I'm not sure exactly why they're so crumbly, but as you saw, some were a lot more crumbly than others, because the one area that we tried to sample in, we failed twice. And then the next time when we found it did look like a more sturdy rock. And they're not all conglomerates are created equal, obviously. So when we found a rock that looked more sturdy but still had all the signs that they wanted to sample, then we were able to get the really nice core too. It wasn't even crumbly at all. But in that one area, everything in that area was crumbly.
Okay. So I like this question. We had a question that says, were most of the good science targets found at the pre-selected locations? In other words, were a lot of the places where you paused and took a sample or spent time examining, were those all pre-selected, or how much serendipity was there as far as all of a sudden you see, oh, that looks interesting over there, let's go check that out?
That happens a lot. So there are some areas that were selected from the high-rise imaging that we knew looked interesting and we wanted to go there. And then our MRO also has another instrument that I can't remember the name of that would sort of could tell us what some of the materials were in the area. And that's why we wanted to go to the margin unit. But a lot of times what happens is every time we drive, we take post-drive imaging, we take a 360 nav cam, and we often take many Z cams. And then suddenly we'll just see something that looks bizarre. We weren't going to Bright Angel. Bright Angel wasn't a spot that we were interested in going to. We didn't even know about it. And then we saw it in one of the Z cam images, and the scientists were like, well, we were going to go to Beehive Geyser, but now we want to go to Bright Angel because it looks more interesting. And then when we got through Dunraven Pass, then suddenly in the distance, we were seeing this area that had really, really dark rocks that we had no idea they were there. So it's really almost 50-50. About 50% is we've looked at this area from orbital imagery and we know where we want to go. And the other 50 is shiny, let's go there.
So one question that I had that when you're talking, you had that one slide early on, I think it was in the SIDA, I probably mispronounced that area. And you had that one image showing that it was almost like a layered intrusion. And you had this differentiated magma that you ended up having these different layers with some different compositions in it. And so I was wondering, is that because and maybe not enough information, but do you think that that's because of the impact, the melt during an impact, or do you think it was from some sort of magmatic activity from the interior of Mars? And how would that speak to the activity that Mars has going on?
Yeah, the crater floor turned out to be much more interesting than I think anybody thought it would be. Seta was incredibly interesting, but then the area around Seta, which I don't think I actually mentioned here, is called Mars. And they're similar, but not exactly the same. And the one thing they don't know, first of all, they don't know where all this volcanic, all these volcanic rocks came from. Not 100% sure on that. And they're also not 100% sure about this Seta and the Mars relationship. I think it might have said it on my slide, but I don't think I actually said it. And it's just a mystery, like, yeah. So the Mars formation and the Seta, they're similar, but not exactly the same. And why? There's still a lot of why. I mean, we're building a really good story about the history of water and its alterations in the Jezero crater, but we're just still not sure about a lot of things. And so we know there's variable layering and it's generally the same composition on the crater floor, but the Seta and the Mars are different enough that it's interesting. So I don't know.
Yeah, I guess the question comes down to, how dynamic is Mars and how dynamic was Mars, in the various ways. And I'm looking forward to, learning more. I hope we get those samples back so that we can, delve more into the story that the rocks have to tell us.
Yeah, me too, because we've only got a portion of it. And I think until we get rocks back, we'll always only have a small portion of it. But as we get more data and more scientists look at the data that we have, because all of the data that comes down from the rover is released out to the public. And so you've got all these colleges, these academic institutions that are taking our data and people are studying it. And the more people study our data, because a lot of the scientists on the project have time for some science, but they're also doing operations. But as the years go by, what we'll see is this picture come more clearly into focus of exactly what has happened in Jezero Crater. And that's going to be fascinating. I saw that when I was on Cassini. At first, we just had a lot of information. We didn't know what it all meant. And the same thing with Curiosity. But as time goes on and more academic folks and scientists get their eyes on this data, then we'll start getting some of those answers.
Well, thank you so much, Kim. This was phenomenal. I can't wait to speak more with you next week about this during our Cosmic Conversations. If you have not registered for that, the link is in the Zoom chat. You can go ahead and sign up. It is going to be on July 2nd, 5 p.m. Pacific, 8 p.m. Eastern. Thank you so much for coming. And of course, to our Zoom attendees, we do have June's survey link in the chat. You can also select that and just let us know what you thought about tonight's webinar. And that is it. We will see you again in August, and keep looking up. Enjoy your July.
Thank you, everyone. Good night.
Good night.
Thanks.
All right, we are all done.
Thank you, Kim.